in this molecule? Eight. Okay, you guys put a bunch of eights in the chat box. That's exactly right. We have 5 carbon atoms that are part of the ring system with my laser pointer. 1, 2, 3, 4, 5. And then we have an additional 3 carbons that are kind of sticking out of the ring. These are called methyl groups. You guys don't need to know that just yet, but you'll need to know it soon. So you can start getting used to that word. Methyl means CH3, so you've got these methyl groups sticking out to the side. So what about hydrogen atoms? Think about all of the different carbons, and remember any carbon where you can't see a full octet. If you can't see the full octet, then that means that the rest of that octet is filled with bonds to hydrogen atoms. That's the rule for line angle drawing. So unless you have some indication that the full octet is there or some formal charge to account for, then whatever is left over that you can't see is filled up with hydrogen atoms. So for example, in the carbon where my laser pointer is, it has 4 bonds to it already, so it has no hydrogen atoms. Same thing for this carbon and this carbon and this carbon. Also same thing for all these nitrogens. Yeah, so you guys are getting the right answer. I see the answer coming through in the chat box. There are 10 hydrogen atoms. So each carbon that's sticking out of the ring, you can see is only bonded to one other thing. That means it needs 3 more bonds to fill its valence shell, which means it has 3 hydrogens. So we got 3 hydrogens on this carbon and this carbon and this carbon. That makes 9 hydrogens. And number 10 is over here on the far right. So if you look closely at this carbon atom, it only has 3 bonds that are shown to other atoms. In this case, they happen to all be bonds to nitrogen. That 4th bond is an implied hydrogen that's sticking out over here. How many hydrogen atoms does that carbon have?
None.
That's right. Good. Great job, guys. This carbon has its full valence already showing. 1, 2, 3, 4 bonds. And then same thing with the carbon up here. Okay, what about lone pairs? How many lone pairs are in this molecule? I'm giving you a hint that this is an overall neutral molecule and that there are no formal charges. Or I always say that, it's not very accurate. All of the formal charges are 0. So how many lone pairs do you guys count in this molecule? Yeah, so there's some 8s coming up in the chat box. That's exactly right. If you look at what would take to satisfy an octet and a formal charge of 0, every single one of these nitrogens would have a lone pair on it. So that makes 4 lone pairs for the nitrogens. And then these oxygens, both this one and this one, would have each 2 lone pairs. So that's another 4. All right, great job. So let's jump right back into where we picked up in the rest of the chapter. I do have office hours today from 3 to 4, and you can find that Zoom link on the syllabus. I have moved the Achieve Chapter 1 homework to Friday. Based on the pace that I went in my earlier section of this class today, I think we're not quite going to make it through all of the rest of Chapter 1, so you're welcome, Jessica. I've moved the Chapter 1 homework due date to be Friday morning. And of course, likewise, that means that the quiz is, of course, not going to be on Wednesday. The quiz will be on Friday. So that Friday quiz will be in class. We are going to probably finish Chapter 1 on Wednesday, and I hope get a jump start on Chapter 2 on Wednesday as well. But we'll wait until we finish Chapter 1 to do the quiz. So now this is going to be Friday, this Friday, February 4th. And we will have... we'll talk a little bit more about the quiz on Wednesday. So I'm going to ask you guys to hold off on all of your quiz questions until Wednesday. All right. I put this slide up last time, but I just want to remind everybody that as you're doing your studying and reviewing, you can, in addition to your graded Achieve homework, there are ungraded practice problems that are from your textbook that I've tried to kind of target you guys towards so that it's not so overwhelming just looking at all those questions. Of course, you can answer more questions or try to answer more questions. So no worries about that. We're going to talk about the quiz on Wednesday. So I'm going to ask you guys to hold your questions about the quiz until Wednesday. Okay. So you can see that we've gone through most of chapter 1 already. Today we're going to focus, actually this wave properties should be black also. We're going to cover mainly these 3 topics here. And these last 3 topics are actually very short and quick. There's just a couple slides each. So we'll get to those on Wednesday. So today we're going to start off with wave properties of electrons. And this is a mistake in my slides, guys. I have it posted here as a review, but you guys, we didn't get to talk through these slides. I asked that you guys review these slides on your own. So I'm going to go through them now. So for wave properties of electrons, this is kind of a weird philosophical thing to have to wrap your brain around, but I'm going to try to do my best to give you guys some ways to think about it. So I'm showing you guys here, and hopefully you remember from around our second class together, that we can represent the probability of finding an electron somewhere and its location with respect to the nucleus. We can represent that probability using a mathematical graph. So for the 1s orbital, that graph looks like this, where the likelihood of finding it closer to the nucleus is high, which should make sense because opposites attract, right? The positive nucleus and the negative electron. And the farther you get away from the nucleus, the less likely it is that the electron's hanging out way out here. So we talked about this amplitude of the wave function, but it turns out that this wave function can exist as a positive version of itself or a negative version of itself. And now we're talking about the sign of the amplitude of the wave function, not the actual charge. We're not talking about a charge at all. We're talking about a mathematical sign. And of course, we have to find easy ways to represent this. So we typically represent this as giving an orbital either a little plus or minus sign. You guys can imagine how confusing that gets because there are a lot of plus and minus signs that mean charge. And here they don't mean charge at all. They mean amplitude of the wave function. So now in kind of more modern day times when we have better access to making better graphics, we typically represent these by different colors or shadedness versus not shaded. Now, these mathematical signs of positive and negative can also be called phases. And I don't want to give the impression that this orbital is either this phase or this phase. It's actually kind of bouncing back and forth from one phase to another really quickly. And one kind of way to think about this is like what's called a standing wave. So if you've ever played a guitar or learned about guitars are another example of standing waves. What I mean by this is say we have something, a string or a mathematical function that's fixed at both ends, but it can oscillate between the up and the down position. So much like guitar strings, right? So if you have a guitar string, it can oscillate either as a full thing or you have different harmonics based on how many kind of breakdown waves, the size of the wavelength, if you will. So, but the size of this wave, so the amplitude has a measure to it. It's highest in the middle, it's smallest near the ends, but it goes up and down in kind of the same amount, right? And it flips back and forth between these two. So that's the oscillation, right? And the size of that oscillation, whether it's a big one or a little one, is the amplitude, and how fast it oscillates is the frequency. So it turns out that those same types of words, amplitude and frequency, they can be used to describe electrons and the energy levels of electrons. So you can see here, we've got a positive wave function and a negative wave function. And what I'm trying to connect for you guys is that these are kind of flipping back and forth, right? So we've got a blue phase orbital, but that blue phase orbital is really like flipping back and forth in its phase. Okay. We've looked at the 1s orbital for this with essentially a blue phase and a green phase and going back and forth, but it's not just the 1s orbital. We can also do this for a 2p orbital. We can do this for any orbital, really. And basically, wherever the wave function is above the plane, like above the x-axis, then it'll have one phase sign, and wherever it's below, it'll have the other phase sign. But even though it has some spots that are below and some spots that are above, it still has the capability to oscillate, just like the harmonics of a guitar string, like I showed you on the other slide. So in this case, for our p orbital, we'll have a blue phase on the right and a green phase on the left. Or in the other version, the other sort of oscillation version, we've got a green phase on the right and a blue phase on the left. And you're going to hear me say this a lot. We're talking when we have this plus or minus or the different phase. This is, again, the mathematical sign of the wave function. Is it above or below the x-axis? And these are not representative of any charges. Okay, and then finally, I want to point out where the wave function crosses the x-axis, that means there's zero probability of finding an electron, and that means there's a node. So for the 2p orbitals, that node is right in the middle. And often the phase switches, well, not often, I mean, I think mathematically it's defined this way. The phase switches to the opposite phase whenever there's a node. So if it's green phase on one side of the node, it'll be blue phase on the other side of the node. Okay, I know this is really weird, and you'll see why we're talking about it over the next couple of slides, but I just want to check in and make sure you guys are doing okay with these concepts so far.
I just had one quick question.
Yeah, go ahead.
You said that where you see that the blue line crosses the x-axis, that means that there's zero probability to find electrons?
Yeah.
Okay, I just wanted to make sure I heard that correctly.
Yep, that's right. Whenever you have your wave function crossing the x-axis, the wave function describes the probability of electrons to be in a particular location with respect to the nucleus. Yeah, John, did you raise your hand?
I did. I had a question about that as well. So with the graph to the left, not with the 3D representation, does that mean below, so on the negative part of the wave, that there's a less than zero probability?
Okay, that's a really good question. All right, so you're calling me out on some subtleties of the Schrodinger equation and wave function. So here we go, because John asked. This graph is actually the wave function. So this graph represents the solution to the Schrodinger equation. In order to get the actual probability of where electron density is, you have to square this. So when I'm talking about probability and the electron density, I'm actually talking about psi squared, which, if you imagine squaring something that's negative, it'll end up positive. So that was a great question. Thank you for calling me out on my technicality. What's plotted here is the actual wave function and not the squared wave function. And that's because it's easier to see the phases, the negative and the positive phase.
That makes so much sense. Thank you.
Okay, you're welcome. And sorry if I confused anyone about the Schrodinger equation. Okay, let's get out of Schrodinger land. Oh, one more take-home message. This is the same thing I keep saying. Mathematical signs, not charges, mathematical signs. So, of course, everybody nowadays likes colors better, but in old-timey books and with old-timey chemists, you just need to have an awareness that some people still do use the plus minus. Okay, not that I'm an old-timey chemist, just so you guys know. All right, so let's move on away from the wave properties of electrons and talk about some molecular orbitals, all right? So with molecular orbitals, what we're gonna do is take some of our atomic orbitals and be able to put them together so that we can actually make bonds. So we've talked so far about bonds in terms of the Lewis structures, but that's not a very sort of electron-friendly picture of what's happening, right? We decided we're just gonna use a line to represent electrons. That's not very descriptive. So let's get a little bit more descriptive here. So this should make intuitive sense to everybody, given that you guys have all had at least a year of chemistry under your belts. If we take two atomic orbitals, so for example, these two 1s atomic orbitals, these are hydrogen atoms that are each carrying one proton and one electron, right? So if we bring these two 1s orbitals together, then there's going to be some favorable interaction where they overlap and make a new bond And in fact, one way to think about this is that these atomic orbitals are going to come together to create a new molecular orbital. So this is an orbital that is shared over some portion of the molecule as opposed to being identified just with one atom or another. Okay, so this should make sense that this has some stability associated with it, because if you think about what we just did, we took these two atoms that did not have full valence shells and we let them pair up, which means now they have a full valence shell. So these molecular orbitals are created from atomic orbitals. And so those atomic orbitals don't exist anymore. We took the meat of those atomic orbitals and we used them to make these molecular orbitals. And these molecular orbitals, again, belong to the molecule as a whole, or at least as some portion of it. All right. When we did this, we formed a bond, and we're going to call that kind of bond a sigma bond. This is going to be formed by overlapping orbitals that are directly kind of pointed towards each other. And I want to make this clear, and I'll say it over the next couple of slides. We're bringing together two atomic orbitals, so we need to get out two molecular orbitals. There's a rule about conservation of orbitals that I'll talk about a little bit later. So in addition to our sigma bond that we created, a bonding orbital, we're also creating at the same time an anti-bonding orbital, which is denoted as sigma star. That's an asterisk next to the sigma, but chemists say this as sigma star. So we're creating a sigma orbital, which is a bonding orbital, and also a sigma star anti-bonding orbital. And it's not shown on the slide, but I'll show you on some upcoming slides. If you think about this kind of in a intuitive sense, when we bring these two atoms together and make a bond, we're getting some stability benefit. That means there's some energy stored up in that bond. And that energy that's stored up in that bond is actually the bond dissociation energy. So however much energy it would take to break this bond and return back to when we give each hydrogen atom its electron back and they separate, that amount of energy is the bond dissociation energy. All right, so here's, we just talked about how for the case of two hydrogen atoms coming together, there was a benefit because of filling up the valence shell. But this is another way of thinking about why bonding is good for atoms. If you want to bring two atoms together because they really want to be able to share each other's electrons to try to reach their valence shell, when you bring them closer together, the positively charged nuclei, because nuclei have protons and neutrons, they're going to actually be repelling each other. So what's one way we can kind of manage that or mitigate that repulsion? And that's to let our electrons reside in the area between the two nuclei. And so the having electron density between those two nuclei, forming that bond, is beneficial because it brings some stability, because it mitigates those positive charges repelling each other. Okay, so this is just one way of considering things about bonding, and I'm going to put this in the context also of an energy diagram that looks kind of like this. So what we're looking at here is a graph where we have energy on the y-axis. So the more stable things are further down at the bottom, the less stable or higher energy things are up at the top. And if we start from the right and imagine our two hydrogen atoms that are not associated with each other, as we bring them closer, they start to realize, oh, hey, there's another atom out here that has an electron, and maybe we could get together and share our electrons and be happier. So as they get closer, the energy drops because you're getting a little bit of stability in the system. They're starting to be able to reach out and partially share electrons with each other. And as you get closer and closer and closer until some perfect distance, at some perfect distance, you have maximized the energy benefit of bringing those two atoms close together. You have formed like a true molecular orbital where the electrons are no longer belonging to one atom or the other, but they're shared in a molecular orbital now. And if you keep trying to push them closer together from there, it doesn't work because the positively charged nuclei get too close together and they repel each other. So I should have said this in the beginning, but this x-axis here is the distance between the two nuclei. Hopefully you guys figured that out by what I was saying and the word on the graph. But hopefully this makes sense. So this distance that the nuclei are apart from each other, that gives you the bond length. So in the case of molecular hydrogen, so H2, the preferred bond length is 0.74 angstrom. And the energy difference from sort of a 0 point energy being when the atoms were not connected to each other at all and nowhere near each other, that energy well here gives you the bond dissociation energy. All right, so of course, the distance here and the energy here are important. These are going to be things that will come up every once in a while, but I thought this was a really neat way of thinking about kind of electrons coming together. Someone put in the chat box about what gives the BDE. The bond dissociation energy is the energy difference between the energy level of the two atoms that were nowhere near each other and not interacting. So that's the 0 point energy with the dotted line. And the difference between that 0 point energy and the stability associated, so the drop in potential energy associated with achieving the perfect length of those nuclei apart from each other. Did that make sense, Raven? Okay. All right, great. All right, so let's move on a little bit and see, now that we kind of have done our cartoon version of these ball s orbitals coming together, let's make this a little bit more scientific and a little bit more quantitative, just a little bit. So when we bring these two s orbitals together, we've already talked about, and I've reminded you guys about how we can graph the wave function for these orbitals. When we bring these two orbitals together, if they're the same phase, then they can have what's called constructive interaction, where the wave functions will add together, and that'll create an area in between the two with enhanced electron density. So this is represented up at the top here in a very mathematical, very graphical way. Most people, including myself, prefer the bottom way, which is more kind of intuitive, that you're bringing these two electron clouds close together. And when you do that, if it's constructive interaction, if they're the same phase as each other, then they are coming together to give you a bonding orbital. So this is constructive interactions. And there's also, your book gives you these electrostatic potential maps, and that should show you also that the electron density, I don't like this one because the electron density is really sort of like mostly between the two atoms. This makes it look like it's all over the place. So in fact, ignore this and focus on these ones. Okay, so I've already told you we have to, if we're bringing in two atomic orbitals, we have to create two molecular orbitals. So let's look at the second molecular orbital, the sigma star. And somebody's asked if these three graphs are identical. These are three different representations of the same thing. Okay, does that, I think that might be what you're asking. So this is a mathematical representation, a sort of two-dimensional representation or a three-dimensional representation, and then a cartoon representation. Okay. So what about if they're not the same phase? What if they're the opposite phase of each other when they come together? Well, just the same way that it works in math, if you subtract something that's the same exact size as something else, you get 0. So that's what happens if you have what's called destructive interaction. If we bring together an s orbital that is blue and an s orbital that is green, or in the blue phase and the green phase, then you can see that at some point right in the middle here, they'll cancel each other out and be 0. And so what you end up getting is what looks like this, and this is going to be the sigma star antibonding molecular orbital. So you can see here we've created a node between the two nuclei, and the electron, or the orbital shape, is kind of leaning out away from the internuclear space. And that should make sense if you look at it mathematically up here or intuitively down here.
I have a question.
Yeah, go ahead.
So that means that when you have an anti-bonding formed, it just creates a node.
It just creates a what?
A node.
So anytime you have the two wave functions mathematically cancel out, you create a node. It doesn't have to be in an antibonding orbital. It can be in any orbital, but anytime mathematically you have these two wave functions cancel each other out, you'll create a node. And someone has asked, is there a reason they took that shape? And yeah, the shape has to do with this mathematical representation. And if you imagine the blue and the green canceling each other out, then as you bring these closer together, they'll cancel out in the middle, right? But they'll still exist on the sides. So these different representations are just different ways of showing you guys the same kind of a thing. I want to show you guys a couple of more slides before I answer any questions, because I think they'll become clear as we go a little bit more. So on this slide, what I'm showing you guys is what's called a molecular orbital diagram. This is the same information as what I showed you guys in the last couple of slides. It's just put together in a different way. So here we've got our orbitals showing on an energy scale. We're bringing together these two atomic orbitals. When we bring them together in a constructive way, blue plus blue, we get this bonding molecular orbital, which is sigma. And notice it's lower in energy, and that should make sense because of what we've already talked about with the stability associated with this. If we bring them together using destructive interference, so instead of blue plus blue, we do blue minus blue. And remember, the negative of blue is green in this case. So when we bring together a blue and a minus blue, or a blue and a green, we get this kind of a shape, which is the antibonding orbital and the node in the middle. So you can see there's different ways to represent the shapes, and they're not exactly perfect. So if you look at this we've got two kind of egg-shaped things here. It doesn't look exactly the same as what I showed you over here. And that's just because of how careful or not careful, or how exact and perfectly close people who are plotting these things get to the actual Schrodinger equation. But the gist is the same, okay? And the overall general shape and features are going to be the same. All right. So a couple of other points I want to make about this. Here's where I'm laying out this as a rule. It is a rule. It's a rule. It's a rule. We are going to conserve our orbitals. However many atomic orbitals come in, you have to have the same number of orbitals come out as what you put in. So now we've been talking about bonding and anti-bonding orbitals and creating molecular orbitals out of atomic orbitals. So for right now, when we're talking about creating molecular orbitals, it's pretty much always going to be two orbitals coming in to give us a bonding and an anti-bonding. But this rule is a very generalized rule, and we'll see it applied in a different way in the later slides. Okay, someone's asked in the chat box, are these formations of molecular orbitals one of the reasons why knowing wave properties, phases, etc. is important? I'm going to go with yes on that. Yes, this is one reason why understanding the wave properties and the phases and like where they come from is important. Okay, and someone else has asked, what dictates if it's two of the same charge or opposite charge? Okay, first of all, these are not charges. Remember, they're mathematical signs or phases. And remember in the beginning, I said that it's oscillating like a guitar string. So each of these s orbitals isn't just hanging around as a blue phase s orbital. It's going blue, green, blue, green, blue, green. And over here, it's going blue, green, blue, green, blue, green. And so statistically, half of the time these two come together, they'll both be blue. And half of the time they come together, one will be blue and one will be green. So there's not like, I don't know how to say this. It's not either to the same or to opposite. It's both. There's going to be a situation where they come together where they're the same, and a situation where they come together where they're opposite. Did that help answer your question? Great, thank you. All right, let's see some more examples. Oh, and actually, this is a very important note. Here we're talking about bringing atomic orbitals together to make molecular orbitals. And we're really talking for the time being about the
bonding high bond.
the shape and the shell of those orbitals. And we're not right now talking about whether or not they're populated with electrons. So it happens in this case that each one of these atomic orbitals brought in one electron, and we still have to follow Hund's rule here. So we put our electrons in the lowest energy orbital. And so they're together in that bonding orbital. But for right now, the number of electrons, the placement of electrons, that's not what we're talking about. We're only talking about the orbitals themselves and their shape. So it's essentially talking about like houses, right? We built a house that looks like this, and we built a house that looks like this. And whether or not anybody lives in that house is not what we're talking about right now. Okay, so we've been talking about sigma bonding, where the electron density lies between the two nuclei, right? And I've shown you only so far examples of s orbitals and s orbitals coming together. So they don't only have to be s and s orbitals. We can have other types of orbitals coming together. And so I'm going to show you some more examples of that. So starting with an s and a p coming together. Okay, so this is what it looks like if you bring an s orbital and a p orbital together using constructive interference. We have the blue s orbital and the blue lobe of the p orbital are going to come together, and they're going to create this new molecular orbital that looks like what's shown on the right here, with a larger blue kind of molecular orbital lobe that has a lot of electron density between the two nuclei. And it still has a little green lobe over to the left of the whatever atom it was coming in from the left. So keep in mind, we're making molecular orbitals, which means we're bringing atomic orbitals together to make a bond between two atoms. So each of these black dots represents the nucleus of a different atom. All right, this could be a carbon and a hydrogen, or a carbon and a carbon. It could be any two atoms, but they're two different atoms. And so what we've just done by bringing together this px orbital with this s orbital is to create a sigma bonding molecular orbital that has a little bit different of a shape, because it reflects the shapes of the orbitals that were used to make it. All right, I just told you guys a rule. So of course that was the bonding orbital. Now we need to have an anti-bonding molecular orbital. And so this is what happens if we bring these two orbitals together when the overlapping area are in the opposite phase from each other. And so the green side of this s orbital will cancel out the blue side of this p orbital, and we'll get a node here. And then the rest of this p orbital will still have its electron density over there, or its shape over there. Okay, and again, the bonding orbital is going to always be lower in energy than the anti-bonding orbital, just because of the nature of the stability associated with those bonds. All right, so that's what it looks like if we wanted to bring together an s and a p to create a sigma bond. And again, remember that sigma bond electron density is between the two nuclei. So what about if we want to bring together a p orbital with another p orbital? Well, this one I actually think is more intuitive than the last one. But what we do is we bring them together end to end, head to head, to create a sigma bond, which means that these two blue lobes will overlap in a constructive way to create a bonding molecular orbital right there. And of course, we have to make an anti-bonding one also. So when we bring them together in a constructive way, we also have to account for the fact that they're going to come together in a destructive way. And in that destructive way, they're going to create a new node, because their electron density will have canceled out perfectly in the middle between those two nuclei. So notice that the nodes that were already there in our atomic orbitals are still here in our molecular orbitals. So our bonding orbital now actually has 2 nodes, and our anti-bonding orbital has 3 nodes. I'm gonna let that sink in while I turn my lights back on. Okay. So here is sigma bonding. We've now gone through a PP version, an SS version, and an SP version. Hybridized orbitals can also form sigma bonds. You guys probably don't know what that means right now, but you'll begin to understand before the end of class today. So we'll put that one on the shelf for a moment. And I want to talk now about, we've been talking about sigma bonding, where we're bringing orbitals together with the density between the two nuclei. Now we need to cover what a pi bond is. And a pi bond, which is the other main type of bonding in organic chemistry, is what happens if you bring p orbitals together instead of a head-on fashion in a side-on fashion. So they're parallel with each other. So this should help you remember p for p orbitals, p for parallel, p for pi. Hopefully that'll help you guys remember. And these bonds, when you bring them together, as you can imagine, because their molecular bonding orbital has to have characteristics of their atomic orbitals, the shared electron density is going to end up above and below the internuclear axis. So you can also kind of intuitively, hopefully, see that the overlap is not as direct as with sigma bonding. So pi bonds are not as strong as most sigma bonds in general. And of course, we have a rule. We have a rule that we have to apply. So if we're bringing them together in a constructive way to make a pi bonding molecular orbital, we also have to bring them together in a destructive way to make a pi star or an anti-bonding molecular orbital. And of course, energy is always higher for antibonding. Okay, so I've said this already, but here's just a little pop-up reminder that the electron density is above and below the internuclear axis for pi bonds. And we'll see another way to look at that on the next slide. So this is a cartoon version of the bonding structure of ethylene. So you can see in this Lewis dot structure that ethylene has a double bond between those two carbons. So 4 electrons total are shared between those two. And I want to take a moment to be clear about terminology here. A double bond, when we're sharing 2 pairs of electrons between 2 atoms, that double bond is made up of 1 sigma bond and 1 pi bond. So a pi bond is not a double bond, right? A pi bond is the second bond of a double bond. Some people get a little loosey-goosey with this terminology, but I want to be clear about it for you guys. Also, a triple bond, which involves, of course, 3 pairs of shared electrons. That triple bond would be made up of 1 sigma bond and 2 pi bonds. So you can see in this cartoon version of ethylene up here, we have a sigma bond that is between the 2 carbon atoms, kind of in this internuclear axis. And then our pi bond occurs above and below the plane of the rest of the molecule. And so a lot of times people make this analogy to a hot dog and a hot dog bun, where your sigma bond is a hot dog and the pi bond is a hot dog bun that exists on both sides of that hot dog, right? But it's still just one bun. So that bun is on the upside of the hot dog and the downside of the hot dog. And then that hot dog sigma bond is in the middle. Okay. So we've talked about bringing together 2 s orbitals to make a sigma bond. And we've talked about bringing together a p and an s orbital to make another sigma bonding molecular orbital that just looks a little bit different. So I want to take a moment to point out that these sigma bonds, of course, they occur on the internuclear axis, but I've also talked about how molecular orbitals have to retain some of the characteristics of the atomic orbitals that made them, right? So the molecular orbital that's made with a p orbital has that same orientation and that same directionality to it that the original p orbital did. Okay, you guys with me on that? Now I'm going to blow your minds for a minute. Think about what you know about p orbitals. There are 3 of them. They're the same energy level and they are 90 degrees to each other, right? So if I am telling you that when we make a molecular orbital, it points in the same direction as whatever the p orbital was that helped to make it, and I'm telling you that these p orbitals only point in 90-degree directions from each other, how the heck do we explain the fact that real-life molecules aren't just bonds at 90 degrees from each other, right? So this molecule on the left is methane. Here's the ethylene gas that we just looked at on the other page. And you can see, in fact, none of the angles in either of these molecules is 90 degrees. So how do we explain that, given what we know about p orbitals pointing in 90 degrees from each other and the molecular orbitals that represent sigma bonds pointing in the direction that the atomic orbitals that made them came from? I'm gonna give everybody just 30 seconds to think about that on your own. How do we figure this out? How do we make this happen? Okay, I know that wasn't a full 30 seconds, but I want to keep going. We cannot make this happen. We cannot take simple p orbitals and create molecular orbitals out of simple p orbitals and explain these molecules. So what that means is that everything that I just talked to you guys about is too simple to explain real life. It's overly simplified and it does not account. It's a theory, right? I mean, everything that we're talking about here is a human interpretation of imagining something that we can't see. So it's a theory that does not work to explain real life, which means we need a new theory. So that's where something called hybridization comes into play. And what we're going to do when we do hybridization, we're going to take a step back. So put molecular orbitals up on the shelf for a minute and come back to just atomic orbitals. What we need to do is to take our atomic orbitals and figure out a way to make our atomic orbitals point in more directions than just the 90 degrees than they currently point in. So that's what we're going to use hybridization for. So this is, again, the same picture that I just showed you guys, and a reminder that p orbitals can only be 90 degrees from each other. In order to resolve this issue that our simple s and p orbitals cannot be used to make molecular orbitals that can go in different directions than the 90 degrees that p orbitals go in, we are going to make hybridized orbitals or hybrid orbitals. And notice really big at the top here, hybridization of atomic orbitals. So we're only going to be talking about atomic orbitals for a little while. So take a step back from molecular orbitals. The reason that we're going to do this is because if we make hybridized orbitals, they can point in different directions and they can enable electron pairs to get farther away from each other, depending on the overall geometry needs of the molecule. So there's a name for this theory. It's called VSEPR, or valence shell electron pair repulsion theory. And it sounds complex, but if you break it down and think about each word in that name, it's exactly what it says it is. Valence shell electron pairs. So what we're talking about is electron pairs, either in a bond or as a lone pair, that are in the valence shell of an atom, and how they want to repel away from each other because they're electrons in a bond or in a lone pair. And those pairs of electrons want to get away from other pairs of electrons because of the laws of physics and negatively charged things wanting to get away from each other. So we have to figure out a way to make this theory, which does help explain the geometry of atoms, that these bonds want to get as far apart from each other as they can, with the orbital configurations of atoms. So VSEPR helps us explain the molecular shape of molecules, and now we need to go back and make this work with our conceptions of orbitals. So we're going to go ahead and do that. All right. So one thing I want to take a moment to point out here is that if you have an atom that's bonded to four things, right, like this carbon and methane bonded to four things, the farthest that these four things can get apart from each other is the four corners of a tetrahedron or a pyramid. And like, if you go back to like geometry, like classical Greek geometry, that means that the angles are 109.5 if these bonds are getting as far away from each other as they can. Likewise, if you have three things, so here this carbon is bonded to a hydrogen, and a carbon. If you have three things bonded and they want to get as far apart from each other as they can in a sphere or in any other way, they have to be 120 degrees apart from each other. If you start to move one of them in any direction, you get too close to the other ones. Okay, so with that in the back of your mind, where we're going to start is the hybridization that we need to build if we want to bond an atom to just two things. So if we want to bond an atom to just two things, how far apart can they get from each other before they start to get close again? Well, 180 degrees, right? If you want to have your two arms as far apart from each other as you can, you put them out in a straight line. So how do we do that? Well, we can hybridize an s orbital with a p orbital. So before I get into that hybridization, I forgot the slide design here. Sorry for my little hiccup. This top half of this slide is what we were talking about before with molecular orbitals. Taking an atomic orbital from one atom, an atomic orbital from a different atom, and combining them in constructive or destructive ways to get a bonding orbital or an antibonding orbital. That these are molecular orbitals. So two atomic orbitals coming together to form two molecular orbitals. We can also take a similar concept, but now let's apply it instead of to two orbitals coming together from a distance, let's apply it to two orbitals on the same atom. So we're going to take two atomic orbitals that are on the same atom and combine them together and get two new atomic orbitals that are different than the other ones, but they're all still on that same atom. So here in this case, we're going to combine an s orbital and the px orbital. And you can see when we do that on the same atom, because they're superimposed because they're on the same atom. When we do that, we get a hybrid orbital that if the phases are as I'm showing you here, the positive phases are going to interact positively and give you an increase in electron density over here to the right of the nucleus. And to the left of the nucleus, there's going to be destructive overlap where at some moment in time right here, the positive and the negative are going to cancel each other out perfectly to create a node, right? And then there's going to be a little bit of leftover negative phase orbital over here. So this is a hybrid orbital that was made from S and P coming together in the phases I'm showing here. But of course, we have this rule about conservation of orbitals. So we also have to bring them together in the other phase direction. So you can imagine this for yourself, but the other phase would give a second hybrid orbital that looks like this. These are going to be called sp hybrids, right? They're both sp hybrids, and they're called that because the orbitals that went in to make them are one s and one p. I should say an s and a p orbital, so I'm not trying to use quantum numbers here. One of the s orbitals and one of the p orbitals in this atom came together to make this hybrid orbital. And of course, I'm showing them separately here to make it easier for you guys to see, but they're not separate, they're superimposed. So the nuclei that I'm showing here are on the same atom because we started out on the same atom. So these are superimposed on each other. And now you can imagine that if you have an orbital, an atomic orbital that's mostly pointed out this way and an atomic orbital that's mostly pointed out the other way, you can now use those orbitals to make a molecular bond. So I'll show you an example of that with the last minute that I have left. These hybridized orbitals, though, I just want to point out, they are hybridized, but they are still atomic orbitals. So we used up an s and a p orbital to make our two sp hybrids. There are still two p orbitals in this molecule, in this atom, on this atom, that are unhybridized, and we're just not showing them. So this is the same thing that I just said, showing you the other version of interference a little bit more clearly. And things we've already talked about, how we're going to bring these two together, two orbitals together, the s and the p, to make two hybrid orbitals that are called sp. And this will enable us to build molecules with a 180-degree bond angle, like what you see in acetylene, where this carbon is bonded only to two other things. And yeah, just one more time, again, all of the nuclei that I'm showing you on this page are representative of the same nuclei. The black dots on this page are only one nuclei because we're only talking about atomic orbitals on one atom. So really quick, and I'll pick up on this next slide when we get together again on Wednesday, but here is a representation of showing what this looks like, taking these hybridized orbitals and then putting them into a molecule. So in this case, I'm looking at beryllium, and I'm wanting to make a BeH2. So if I want to bond two things to that beryllium, I apply VSEPR, and I know that those two things want to be 180 degrees apart. So because I'm taking two things, I'm going to take two orbitals, the s orbital and the p orbital of beryllium. I'm going to make my hybridized sp orbitals, and then I'm going to use each of those hybridized sp orbitals in a bond with hydrogen. So this is individually what that looks like. And this is all together what that looks like. So here is your beryllium nucleus. You're showing your two hybrid orbitals, one going out to the right, one going out to the left. And each of those is making a bond with hydrogen. And then one last note before I let you guys go, is that the little back lobes, the little green lobes, are omitted in the drawing by custom because otherwise it would get really busy and really hard to follow and see what's going on. All right, I'm going to stop there. I encourage you guys to review your book and your book for hybridization because we'll talk about the two other kinds of hybridization on Wednesday. And what I'll do is post this full slide set for hybridization, but we'll pick up from here on Wednesday.
Thank you.
Thank you.
I have a question.
Yeah.
I honestly,
It's on Friday, don't forget. Okay, now you can ask your question. Sorry.
it's okay. I'm honestly completely confused on like everything we did today. So what's the best way for me to like try to review this or try to understand it? Because I really did not understand like anything.
Okay, my recommendation to you is to look at my slides while you have the book next to you and use, because a lot of the pictures that I use come right from your textbook. So use your textbook to read about the pictures that you're seeing on my slides also. Does that make sense?
Yes, ma'am.
And for this hybridization stuff, I know this is a crazy thing to say because I just showed you guys SP hybridization. I actually personally think it's easier to understand and more intuitive once you see the other types of hybridizations. So I think, I was kind of hoping to get farther through them today because I think seeing the later ones helps the earlier ones click. But that being said, like, don't worry if you don't have the hybridization part down right now because it is new. But thinking about the overlap of orbitals and stuff like that as a general way, reading your book and looking through these slides, that's going to be your best bet for this. And also going to SI session.
Okay. It's the SI session that I see for this class, I'm in another class.
So Honor has 3 different time slots during the week. There's a Monday slot, a Tuesday slot, and a Thursday slot. Are you booked for all of those?
Oh, I've only seen the ones on Monday. I didn't know that she had ones on other days.
Yeah, he has 3 different sessions, and actually, if you give me a second, I can, if it'll let me back out of this, I can scroll down. All right, here we go. Honor has sessions Monday at 6 p.m., Wednesday at 5 p.m. Oh, hey, I thought it was Monday, Tuesday, Thursday. Great. Honor has a session today at 5 p.m. So you can go to his session. I believe it's in Hibbs 118. Yeah, you can go hang out with him and do some practice problems. And he also kind of re-explains topics again. And then also I have my office hours from 3 to 4 today, so you can stop in then as well.
Okay. Thank you.
You're welcome.
All right. You have a good day.
Thanks. You too. Okay, guys, I'm gonna let y'all go and I'll see y'all later. Bye.